In this very schematic demo, I'm going to quickly demonstrate how you can use Comsol to make a simplified simulation of boiling of potatoes. I'm not going for accuracy here, and if you're one of my students, please note that your task concerns oven-baked potatoes, not boiled potatoes. With that said, here we go. We open Comsol and select Model Wizard. We want to make a three-dimensional simulation, so we simply select that. Next, we need to add our physics model. We are going to model the potato only, treating the boiling water as a boundary condition. So for our intents and purposes, heat transfer in solids is good enough. You find that under Heat Transfer. After selecting Heat Transfer in Solids, we click Add and the right arrow below to take us to the selection of kind of study. We want to see how the temperature of the potato varies with time, so we select Time Dependent, which you find under General Studies. With that selected, we click Done. A potato can have a somewhat irregular shape, but let's choose an ellipsoid. If geometry is not selected, go ahead and select geometry and then choose the ellipsoid tool. Just like a sphere can be defined by its radius, an ellipsoid is defined by 3 semi-axes. Thus, if we imagine we have a small fresh potato with outer dimensions of about 4 centimeters in 2 directions and 6 centimeters in the third direction, you have the semi-axes 2, 2 and 3 centimeters respectively. Now, if you're one of my students, you know the weight of your potato, and by coming up with a reasonable estimate of the potato density, you can tweak the semi-axis until you get a good fit. After we have entered our values for the semi-axis, we click Build All Objects and we can see our potato. Time to enter some values for heat transfer characteristics. In the physics heat transfer in solids, we currently have 3 items: solid 1, initial values 1, and thermal insulation 1. The first 2 have a fully filled in symbol. This means that the values in here are valid for the entire domain, the entire inside. In solids 1, we are to enter 3 things: thermal conductivity, density, and heat capacity. Currently it says from material on all 3, but there are 2 problems with that. Firstly, we have not chosen any materials yet, and secondly, Comsol does not include potato as a material. Thus, we need to change these to user-defined. If you're one of my students, you will need to come up with reasonable values for these 3 characteristics, but in this demonstration I will only put in approximate values for water here. So 0.6 watt per meter in Kelvin as the thermal conductivity, 1000 kilogram per cubic meter as the density, and 4200 joule per kilogram in Kelvin as the heat capacity. It seems reasonable that the characteristics for potato is in the same order of magnitude as for water, so at least my quick and dirty estimation is not pure nonsense. In initial values 1, you need to enter the initial value for the temperature. Here you need to make a reasonable assumption. For the sake of this quick demo, let's just say that the potato came from a fridge holding 4 degrees centigrade. Please note that if you look under domain selection within initial values 1 and solid 1, domain 1 is chosen by default. Whatever values you enter are only applicable within the chosen domain. Currently we only have one domain, the potato, so that's all fine. Under thermal insulation 1, we have by default 8 boundaries selected. Currently, our potato is thus thermally insulated from the surrounding world. That's not what we want. To fix this, we control-click on Heat Transfer in Solids and select Heat Flux. A new item, Heat Flux 1, was created, and inside we see that by default we got a general inward heat flux of 0 watt per square meter and that no boundaries are selected. That's not what we want. Assuming that water surrounds all sides of the potato, we want to include all boundaries. Furthermore, a better way to specify the heat flux is to either use nucleate boiling heat flux or convective heat flux. To make this demo more similar to the simulation of an oven-baked potato, let's choose convective heat flux. When using convective heat flux, we need to specify the heat transfer coefficient and the external temperature. The external temperature is the temperature outside the potato, that is, the temperature of the boiling water. Let's say that that is 100 degrees centigrade, so 373.15 Kelvin. The heat transfer coefficient is determined by the water. Let's for simplicity say that the heat transfer is 100 watt per square meter in Kelvin. We have now entered all the data we need, and it's time to set up this simulation. First, we need to decide on the spatial resolution of our simulation, that is the mesh. Let's just select normal element size and physics controlled mesh and click build all. Please note that the smaller element size you choose, the longer time your simulation will take. However, if you choose a too large element size, your calculation will become inaccurate. With the mesh decided, we now just need to decide the length of the simulation. Since one can typically boil potatoes in something like 20 minutes, let's select 30 minutes to be on the safe side. With all this done, we click compute and wait. The result graph we get is not terribly interesting, as we only see the surface temperature at one specific point in time. More interesting is to see how the temperature varies throughout the potato and how the coldest point in the potato changes temperature over time. To see the inside of the potato, we control-click on results and create a 3D plot group. In this 3D plot group, we select a slice plot. If we now click plot, we by default get 5 different planes through the potato in a default direction. You can change the direction and number of these planes and click plot again to see the result. If you're one of my students, we want you to hand in a slice plot with one plane along the longest dimension of the potato. To see how the coldest point in the potato warms up over time, we need to create a domain probe. We do that by within component 1, control-clicking on definitions and select probes and then domain probe. By default, domain 1 is selected and the type of probe is an average. We change average to minimum and then click update results. Comsol then creates a probe plot group where we can see how the temperature increases with time. If you wonder about the small glitch in the beginning of the simulation, that's just some numerical instabilities at the onset of the simulation. You can learn more about that in advanced courses on numerical methods. Before we end, I just want to show you what happens if we add another object that intersects our potato. Let's create a very thin cylinder that goes straight through the potato. Now when we go into solid 1, we see that we have more domains. In my case, we now have 4 different domains, numbered 1 through 4. If you click on the digit 1 in the list of selected domains, you see that that domain is the potato. Domains 2 and 4 are the parts of the cylinder that is outside the potato. But what about domain 3? Well, click on the digit 3 and turn on transparency. You now see that domain 3 is the part of the cylinder that resides inside the potato. Why is this important? Well, if this cylinder is made of another material than the potato, we will need to create a new solid in our physics, and in that select all domains that are made of the cylinder material. When doing that, it is often easiest to first select all domains and then deselect whatever domain should not be included.